सॉफ्टवेयर, अच्छा दो बातें, एक तो ये कि नस की तरफ से हमें हिदायत दी गई है कि हम इंग्लिश में लेक्चर दें। शायद उसका थोड़ा बहुत असर आपने रिसेंट दिनों में देखा होगा, शायद ना देखा हो। दूसरा ये है कि ये सॉफ्टवेयर जो है ये अंग्रेज़ी समझता है, तो इसलिए मैं ज़रा अंग्रेज़ी में बोलूँगा। तो थोड़ी सी आप लोगों से रिक्वेस्ट है, आप लोग सवाल ज़रूर करें, शर्माए ना, लेकिन थोड़ा सा अंग्रेज़ी में अगर करने की कोशिश करें, उससे फ़ायदा ये होगा कि मैं भी थोड़ा सा अंग्रेज़ी के मोड में ही रहूँगा, ठीक है? क्योंकि मतलब पाकिस्तानी चेहरों के सामने देखते हुए अंग्रेज़ी बोलना इतना आसान मेरे लिए नहीं होता, थोड़ा अननेचुरल मुझे लगता है, लेकिन मजबूरी है। ठीक है जी, तो रेडी, स्टार्ट कर लें। Okay, so today's topic is minimum spanning tree, so it's a new topic. So we'll first define the problem and we'll start from the very beginning, what a tree is, then we'll define what a spanning tree is, then we'll define the minimum spanning tree, and then hopefully towards the end of the class we'll start exploring how to solve this minimum spanning tree problem. I'm pretty sure we won't be able to cover a concrete algorithm, but I'll give a general guideline that how any algorithm that correctly computes a minimum spanning tree, what principle it has to follow. So what is a tree? So many of you would think of a tree as something having a root, multiple child, and that's how we have been talking about it in the class, but that is called a rooted tree, if we go into more specific. Generically, a tree is nothing but just another type of graph. Okay? So it's nothing but just a graph, but it is a graph that is fully connected. So it's not like that it's disconnected, and it's acyclic, so there are no cycles inside it. So here is an example of a tree. You can see that every node is connected with every other node. We can, for example, go from E to say C, or from D to say F, or we can pick any two nodes and we can have a path between it. Okay? It can be multiple paths, it can be a single path, and there is no cycle in it. So this is basically what a tree is. So a tree has a few properties. Number one is that a tree has exactly V minus 1 edges. Okay? So there are V vertices and we need one less edge to connect all of them together in some manner. Okay? So it will always have V minus 1 edges, and each pair of vertices has exactly one path between them. So it's not like that from D we can have some path over here that will take us to F. We can only follow one particular path.
So if there are more than one path, then it will become cyclic?
It will become cyclic. So if we have two paths, so that will mean that something will go over here, something will connect over here, so that automatically creates a cycle. Okay? So if it's connected, it doesn't have a cycle, it's a tree. Okay? So understand this first of all. So if exactly your point, if a connected graph has a cycle inside it, just like over here we have multiple cycles, so it's not a tree. And you can also count the number of edges. It will be more than V minus 1 edges, and there can be multiple paths in it. So if it's a tree, that means there is a single path from between every edges. So like all these three statements are equivalent in one way or another. Okay? So when we say it is a tree, the other properties automatically follow. So this is not a tree, and we can see that we have multiple paths to.
So there are 4 cycles, right?
Huh?
There are 4 cycles in this.
So one cycle is here, one cycle is here, one cycle is here, another cycle comes around over on the outside. So yeah, I think you are right. There are 4 cycles in it. So in a way, a cycle, in some situations, a cycle is not needed. It's an unneeded edge. Okay? And minimum spanning tree addresses those kinds of situations. So now is what a spanning tree is. So we have defined a tree. So now we are narrowing it down to a spanning tree. So a spanning tree is calculated from a graph that has cycles in it. So from this graph we delete some edges such that there are no cycles and it becomes a tree. So this is a graph, it's not a tree, it has cycles in it, and if we delete some edges, the cycles are removed and what we get is a tree. Any questions so far?
Sir, which edges needs to be deleted? Like
There are many possibilities. So in a spanning tree there are many possibilities.
so we just have to make a acyclic graph, whatever possibility we choose.
Yeah. So as far as a spanning tree is concerned, we just need to break a cycle. So if we break the cycles, all the cycles, so it will get us. So there are multiple options how to break a cycle. So this is a cycle, so we have to remove one of these 4 edges. Okay. So similarly. So there can be a large number of possibilities. For one graph, there can be many spanning trees. So a weighted graph, I think you all know a weighted graph is just another graph that has a weight associated with each edge. A weight is basically a number. It can be a real number or an integer. And so this is an example of a weighted graph. And these weights we have discussed a few times that they are used to represent something useful in the real world. So for example, it can measure the friendship between 2 people, or it can represent the distance between 2 cities, for example, Peshawar and Lahore, or Islamabad and Lahore, or some other thing. So minimum spanning tree is then a special type of spanning tree. Okay? So a minimum spanning tree is a tree. It's also a spanning tree, but it's a special type of spanning tree. Okay? So first of all, it's a acyclic subset. So we are deleting. So from this overall edges, we are selecting a subset of edges that we are calling T in this slide. So these are edges. From the existing edges, we are essentially deleting some edges and retaining some edges. So T are the retained edges, such that we get a tree, we get a spanning tree. So it's a spanning tree, so it spans all the graph. So like every vertex of the graph is touched by some edge. That's why it's called a spanning tree. It kind of spans the whole graph. So it's a spanning tree, and it's not just any other spanning tree. It's a spanning tree such that the total weight of the tree, if we sum the weight of each edge in the tree, the weight that we get is the minimum possible out of all the possible spanning trees that can be computed. Let me repeat it again. For a single graph, let's say we have 10 spanning trees that are possible. Out of these spanning tree, if we add the weights of each edge of each spanning tree, we'll get a total weight. From these total weights, we'll select the spanning tree that has the minimum possible total weight. So, a minimum weight spanning tree or a minimum spanning tree, that's why it's called a minimum. So it's a spanning tree that has a minimum weight. So all that we, in simpler words, all that we want is a tree that spans the whole graph and the total weight is the minimum possible. Should I explain this further or is it clear?
So just could you give a small example?
Yeah, sure. So this is a cycle, a simple cycle. How many trees are possible?
Two.
I think three.
Yes, sir.
So one is like something like this. The other is something like this. And the other is one. And I think three if I'm not mistaken.
Yes, sir.
So let's sum the weight. So what is the weight of
Three.
this thing? 3. What is the weight of
Five.
this? 5. What
Four.
is the weight of this? So which one is the minimum
Three.
spanning
First
tree?
one. First one.
So this is the
Minimum spanning. So is there any formula to calculate the number of possibilities which will be derived from of spanning tree? Is there any?
No, it depends on the graph. We can get a number form. So, but it's exponential in a very connected graph because like each vertex is connected to almost every other vertex. So, essentially for each vertex we can pick out of v minus 1 edges, just one edges. So for each vertex we have v minus 1 possibilities of which edge to retain. And then for each vertex we have the same possibilities and then we multiply all of them together and we get the total number of spanning trees. But it depends on how many edges are there in the original graph.
So, sir, basically we are minimizing the computation using minimum spanning tree
Yeah, we are minimizing the calculation,
computations, or we can say it's a pruning process.
or we are trying to find something that is mapped or can be modeled as a minimum spanning tree. So for example, I want you guys have a social network between you and there are probably cycles in it. So I want a small subset and many of you probably don't like each other, kind of hate each other. So let's make a graph that is like hatred, the weight represents hatred. So I would like that I get a remove the edges so that the overall hatred in the class removed becomes lower. So I'll find, okay, this guy and that guy hate each other a lot, so I kind of fix their friendship or something. But right now we are studying it at a more theoretical level, not at an application level. Okay, so this is a graph, a weighted graph. It has many cycles inside it. So just imagine how the minimum spanning tree will look. Which edges will not be included most probably? Yes.
F2, F2 and 3.
Yeah, so for example, I would say that over here we have a cycle and there are two edges of 3. 3 is a heavy type of edge, so we can
So we can move.
remove at least one of them. So our emphasis, so whenever there is a cycle, the heavier edge we will try to remove. So this is one possible. The blue lines represents the edges that are included in the minimum spanning tree. The gray edges show those that are left out or removed. So over here you can see that many edges of weight 3 have been left out. As many as they could. Of course, we have to include either this or this one. Otherwise, this node will not be connected. Okay? So we have to connect it, still have to connect it. So it's not like we just remove all the maximum edges. We have to make sure it remains connected.
Sir,
Yes.
if we have to find a path from I to J, so we would have to go all the way around, like from F, B, C, G, and
Yeah,
then J.
in the minimum spanning tree, so it will be a very long way to go. Yeah. So it's not used for the shortest path computation. That's the point. It's used for different type of calculations, for different type of problem. There are many shortest path algorithm. We'll look at the Dijkstra also. There are many others also. This is a different type and it has a different aim. So let's not think like it's what is it doing. Okay, so is the minimum spanning tree a unique?
No.
When I say unique, I mean, is there one correct answer or can there be many possibilities? So for example, this is a minimum spanning tree and another minimum spanning tree will probably be that I swap this tree with this. So I include this edge, but I remove this edge. So, and similarly. So for example, here's another possibility that is shown. So there can be a number of possibilities, more than one. So it doesn't have a unique answer. A sorting algorithm has a unique answer. For a given input array, we only have one correct sorted sequence. But in this problem, we can have many correct answers. But our aim is not, number one, to find all correct answers, but to find one of the correct answers. So the computation problem that we will be studying is that given an undirected weighted graph G, find the spanning tree out of all possible spanning trees whose sum of edge weights is the minimum possible. So concisely this is what we want to do. So the input graph is the original and the output is the minimum spanning tree. All vertices will remain there. So we won't be removing any vertex, we will be just removing edges. So from the look of it, just like your question, one way to do it is that we find all possible spanning tree and we compute the weight and select the one with the minimum weight. But this will be a very large number, just like you asked that there are many possibilities and it will be near exponential, if not exponential, for most of the graphs. So it's not a really So it's not a correct way to do it. So it will be exponential, so we definitely need a better way to do this. So coming to the better way, every algorithm is based on some intuition by some researcher in some corner of the world. And that basic intuition is what the algorithm is built around. So the intuition behind the algorithm of minimum spanning tree is this. Suppose we have a input graph, imagine any graph, okay? And we divide the vertices into two groups. So some vertices come here, and there are some other edges that connect the vertices inside this group.
So this distribution needs to be equal.
No. Even one vertex can be there and all the rest can be here, or it can be equal, or it can be 75%, 25%, or 80%, 20%. So that's not a condition. Okay? So the edges, there will be edges between this group of vertices, and there will also be some edges that connect these groups of edges. But there will be some edges that connect the vertices from this group and this group. Otherwise, it will be a disconnected graph. So there are some edges. It can be any number. So I'm assuming a k number. So out of these edges, which will be part of an MST?
With the minimum height.
With the minimum width. Excellent. And why is that?
It will give us minimum sum of spanning tree.
Now, because a tree is connected, do we remember this? Connected. So let's call this V1 group and let's call this V2 group. So there must be at least one edge between V1 and V2. Yeah, so far so
So,
good.
so
Otherwise, it won't be connected if there is not a single edge in the MST. So in the MST, there must be an edge.
so what if the edge with the minimum weight lies in one of these groups? Then what?
I'm talking about the cross group edges. I'm talking about these edges. This is connected. This will be connected some way in the minimum spanning tree. These nodes will also be connected in some way. But these two group of edges will also be connected by at least one edge, right? We need one edge
Yes,
to
sir.
connect any group because there's always a path from a vertex to another vertex. It's not a disconnected graph. Okay? So we have to include one edge. Which edge do we include to form a minimum spanning tree?
The minimum one.
The minimum weight edge. So minimum weight. So this is the whole idea. So if you understand this point, you understand the logic behind the algorithm of minimum spanning tree. Who got this point somewhat or clearly? Okay. I'll just repeat once more. So if we divide the input graph into two group of arrays. Some edges will be passing from group 1 to group 2. Okay? Out of all these edges, we need at least one edge to be included in the minimum spanning tree. Since we want a minimum weight spanning tree, so obviously the edge that we need to select is the edge that will have the minimum weight. So this is so we'll just go through some definitions and then I think we can end for today. So I was talking about two groups, so I will now more formally define it. So in graph theory, a cut in a graph is two groups of vertices. One is the set S and one is
Minus.
all the vertices except those in S. Okay? So that's V minus S. So a cut of an undirected graph is a partition. So it creates a partition. So when we cut the vertex, it creates a partition, just like the partition of, I would here say, North and South of Korea. So this is a graph, and there are no weights being shown here because the emphasis is not on the weight but on the partition and cut. So this is our group S, the dark one. Okay? The light one are the V minus S group. Okay? And the partition, so the boundary between these two groups is something like this. Okay? What is the boundary? The boundary is all those edges that connect a gray vertex with a black vertex. Okay? So over here we have a gray vertex, black vertex, gray vertex, black vertex, gray vertex. So if you look, the boundary passes through where the black and gray. So this is what I was meaning by
Partition.
two parts in the earlier graph. So more formally, this is what it is. And we say that an edge E U of V crosses the cut as V minus F if one edge is in S and the other is in V minus S. In simpler words, an edge crosses a partition if it connects a gray vertex with a black vertex. Okay, that's what a boundary is. It connects two provinces or countries or